Hello, good morning. Today we are going to study the influence lines. From here, we just finished in our last lecture influence line for beams. I understand that it is a very difficult time for not only Bangladesh but also for all over the world. The entire world is going to a huge crisis of COVID-19. The deadly virus is spreading exponentially, like the infected people. Now it's over 600,000 and expected to be a million within 4 or 5 days. So it's a crisis, but still we have to move on from where we are. I understand it's not easy, but still we can try. Time is valuable and time is important for all of us. Anyway, we just started the influence line for beam problem. It's example 6.2. You will find it in your lecture note, page number 33, example 6.2. In the problem, it is asked to construct the influence line for the reaction at A, C, and E, the shear at D, the moment at D, shear before and after support C, and moment at point C. So if we look at the problem, it's actually 3 supported beam problem with an internal hinge. The supports are hinge at A, like pin support, CD, that's a roller support, and there is internal hinge at B, and there are other points like D. You are asked to determine the shear force, influence line for shear before and after the D. That is new in this lecture. So first of all, we have to determine the influence lines for reaction at A, C, and E. If you look at the board, I have already drawn the influence lines for reaction A, C, and D. First of all, we have to look at reaction A. At point, the support is actually inclined by 90 degrees, though it looks like a fixed support. Sometimes we use the fixed support like this, but it's a pin support. You can clearly see the pin, circular pin. Okay, so next is the at reaction at A. When it started from point A, it's just one unit force here, on kip per kip, you can say, or kilonewton per kilonewton on. Then it's going down, and when it comes to at B, it's a 0. This is because the first beam AB and another beam is BCE. AB is dependent on BCE. BCE is an independent beam, okay, but the AB is dependent on BCE. So when the force lands on the other beam, there is no influence on beam AB. That's why it comes to 0. The influence comes to 0 when it lands at B. So it is just on kilonewton per kilonewton. This is meter, so we should use the kilonewton per kilonewton. So next is your reaction at C. Reaction at C. So if you calculate here, will come 1.33. 1.33. How you will calculate? You will calculate it many times, because when it comes on kip here, so at reaction at E, and reaction for this beam, it will be highly compression, and in the reaction at E will be as a tension. So this is like a cantilever beam. on keep is here. So this is 1.33 here. When on keep load comes to at C, the reaction will be just on keep. Okay. At reaction at E, starting from 0, because there is no influence when the on keep is at A, then it is decreasing, because I already told you, if you have a load here on keep, say at the middle of this beam on keep, maybe here is 0.5, here is 0.5, here is also 0.5. But if you put a load of 0.5 here at E, it will be a tension. So tension point, or whatever it is, it may be calculated. It has to be calculated like this: 0.5 multiplied by say 3/4, 0.75. So that force will be here. When it comes to B, up to B, it's decreasing. After B, the on-keep load lands on the same beam BCE, then it's going to increasing, and when it comes to C, it's 0. It's like a cantilever beam, and it just increasing. At E, it will come like on-keep. But keep. So that's how it's working. I believe you understand. This is like 1/3. Okay. If you draw a line here, this should be 1/3. Keep per keep. You have to understand the mechanism. You have to actually know how to separate the beams. First is a beam is AB, and the remaining beam is BCDE. So BCE beam independent, and AB beam is dependent on the BCE. That is how it's working. Okay, we'll go for the other part, like B, shear, moment, and shear left at D, right at D, and moment at C. Before that, we just close.